typical reactions, right? We have a reactant number 1 reacts with reactant number 2. And these reactants, they react, of course, and they make products. Okay, now in so doing, let's say that reactant number 1 gets oxidized, right? If it gets oxidized, it's producing electrons, a lot of electrons. Well, reactant number 2 gets reduced. It's accepting those electrons and producing these products. That's what's occurring with every single electrochemical reaction. Now, what is the power, the true power in electrochemistry? The true power is that these reactants, reactant number 1, reactant number 2, all compounds, they have different abilities in giving up electrons. They have different abilities in accepting electrons. So energetically speaking, some compounds are more spontaneous than others in being oxidized. Some compounds are more spontaneous than others in being reduced. Well, what does that have to do with anything? Okay, this is bad. You do not want rust. How could you stop rust? Well, take a look at rust. What is it? You have iron solid. That's, your metal. What is rust? Well, at some point, iron is getting oxidized, right? Iron is getting oxidized, its oxidation is getting more positive. Let's find a metal and put it on that boat. This metal has to be something that is more spontaneous than iron in getting oxidized. And if you find that piece of metal, if you can find something like that and put it on the boat, it's going to oxidize before iron will. So you won't have any rust. At least you won't have any rust until all these pieces of metal are gone. So remember, oxidation is where the anode occurs. So they call these sacrificial anodes. And we'll talk more about this coming up here. But all that information can be obtained in a table like this, the standard reduction potentials. Okay, let's start out with calculating equilibrium constants from cell voltages. Here's our expression. Okay, the standard cell potential is equal to 0.0592 over n log of k. Well, what's this n? Do you remember, to get E0 cell, right, we took two reactions, we added them up, and we got an overall reaction, and we had our E0s over here, and we added them up, and that's how we got E0 cell. But in getting this overall reaction, what did we do? Do you remember what we had to get to cancel? We had to get those electrons to cancel. Right? So let's say we had to multiply the top one through by 3, the bottom through by 2 or something, but the point is that 6 electrons had to cancel for us to get this overall reaction. If 6 electrons canceled, that's what n is. N is the number of electrons that cancel to get this overall reaction. Okay? So let's do a little math here. Let's see if we can rearrange this expression to get k. So let's bring the n and the 0.0592 over first. So the E0 cell, that would be times n, divided by 0.0592 equals log of k. Now, what's the inverse function of log? The inverse function is 10, right? So raise both sides to the 10 power, we'll have our answer. So what equals k? 10 to the E0 cell times N all over 0.0592. So all of our electrochemistry equations so far are right here. Let's take a look at this first question. All spontaneous or naturally occurring reactions have E0 cell values that are, okay, now what up here has something to do with spontaneity? Gibbs free energy. We want a Gibbs free energy to be negative, right? Okay, if Gibbs free energy is negative for spontaneous processes, that means, well, N is just a number. That's the number of electrons that cancel. That can't be positive or negative. F, Faraday's constant, not positive or negative. So it's already negative with our negative sign. So E0 cell must be positive for us to get a negative Gibbs free energy. So the more positive E0 cell is, the more spontaneous that reaction is. So that's huge. That means when you look up here, here's a positive E0, a positive E0. Which one is more spontaneous? Well, the bigger positive number. Next one. When given a reaction, which equation above is the easiest way to obtain a value for E0 cell for the reaction? Okay, you probably already know, but let's just give you a hint here. Let's say we're given a reaction. Here's an overall reaction. Some reactants, go to products. Well, how'd you get it? Well, you add up two half reactions. That's how you get it. Find out what the E0s are for those two half reactions. Add them up and get E0 cell. That's exactly what this expression is telling you to do. How do you use this equation to find E0 cell? Well, we just add up E0 cathode plus E0 anode. And remember, the zeros mean that as long as we're at standard conditions, 25 degrees Celsius, 1 atmosphere, all the concentrations are 1 molar, okay. This is an important point. The more positive or negative the values of these E0 cathode and E0 anode and E0 cell are, the more spontaneous and aggressive the half reaction. The more positive. Remember, we said to make E0 cell a big positive number, that means it's going to be a spontaneous reaction. Well, to get E0 cell a big positive number, E0 cathode should be a big positive number, E0 anode should be a big positive number, and we get E0 cell to be a big positive number. Okay? So the more positive these values are, the more spontaneous and aggressive the half reaction will be, or the reaction overall. And the blank K will become. So remember, the more spontaneous a reaction, that means that, hey, you wait around long enough. We don't know how long you got to wait, but it's going to end up. Nature's going to have that happen. It's going to have it happen strongly if it's very spontaneous. So that means you're going to end up with a lot of product. That means the equilibrium constant would be huge because they're products over reactants. Investigating the chemistry in tables of standard reduction potentials. If all the chemicals in a table of standard reduction potentials were mixed in the same solution, some reactions would occur much more aggressively and predominantly than others. Sure they would, because look at their different E0 values. Some are much more positive than others. In a table of standard reduction potentials, like that below, reactants are always being what? So here's our table of standard reduction potentials. The reactants are always being what? Notice the electrons are always on the reactant side. +2, tin +2 to tin 0, lead +2 to lead 0, right? They're being reduced. And well, they should be. It's a table of standard reduction potentials, right? So reactants are always being reduced. So the reactants are always oxidizing agents. Let's try a few. In the table of the standard reduction potentials to the right, only this part of the table, circle the best oxidizing agent. Oxidizing agents get reduced, so that means we have to find the reactant with the most positive E0. right? So find a reactant. That means it has to be on this side with the most positive E0. Well, it has to be iodine solid. Next, place a box around the best reducing agent. Reducing agents get oxidized, right? So we need to pick, and remember, only the products here get oxidized, Pb to Pb plus 2. So we have to pick a product with the most positive E0. And remember, when we're flipping these half reactions, we have to flip the sign. That's why I said most positive. So flip all these half reactions. Chromium solid, it's going to be a positive 0.74. Order the following oxidizing agents by increasing strengths under standard state conditions. 1 molar all solutions, 1 atmosphere, all gases, 25 degrees Celsius. This just means we can use the tables. That's all that means. Don't let all that information confuse you. That's just standard state conditions. Okay, these are compounds. They're oxidizing agents. Order them in order of increasing strength. If they're oxidizing agents, where do you look in the table? You look in the table for reactants, because reactants in that table are getting reduced. And if you're an oxidizing agent, you have to be getting reduced. So let's find oxygen as on the reactant side. Write down its potential. Cadmium, sulfate. And this part about in acidic solution, that just means a lot of H plus is present. And that kind of supposed to help you find the appropriate half reaction. So oxygen in acidic solution. So here's oxygen gas, but a better one is up here. It's even more positive. Oxygen gas in acidic solution. So let's pick this one. Positive 1.23 volts. Cadmium ion. Cadmium ion is down here. Cadmium is getting reduced, so cadmium, oxidizing agent, negative 0.4 volts. Sulfate in acidic solution. Here's lead sulfate, but that's not sulfate in acidic. Here's a sulfate in acidic solution, positive 0.2. So order them in order of increasing strengths. Cadmium is the weakest, then sulfate, then oxygen. That's the order of their oxidizing agent strength. Consider the reducing agents. Which is the strongest one? Which is the weakest one? So if they are reducing agents, that means they have to be getting oxidized. So look for these compounds as products, because they have to be getting oxidized. So let's find and write down their potentials. Copper, Cu+. So find it on the product side. Here it is. Cu+, going to Cu plus 2. We need to flip the sign. Remember, oxidation, half reactions, got to flip the sign. So negative 0.15. Nickel solid. Find it on the product side. Nickel solid, flip the sign, positive 0.25. Iron solid, find it on the product side, flip the sign, positive 0.44. So which is the strongest reducing agent? It's going to be the one that's the most positive, iron solid. Which is the weakest? It's going to be the most negative one, Cu+. Iron rusts because of the half reaction marked with an arrow. So you see it, there it is. and another half reaction. Write both of these half reactions. Okay, let's write this first one. Oxygen gas and 2 moles of water and 4 moles of electron produces 4 moles of hydroxide. And the E0 is a positive 0.4 volts. The other half reaction is what? Well, what is this material? It's iron, right? And it has to be getting oxidized because we already wrote our reduction reaction. So find iron as a product. There it is. Flip the sign. So positive 0.44 volts is the iron. Iron solid goes to Fe plus 2. Iron solid goes to iron 2 and 2 electrons. Using the table of standard reduction potentials, select a cheap metal to use as a sacrificial anode, which will electrochemically react much more intensely than iron and therefore protect the iron surface from rusting. What can we use instead of this? Something that is more positive than 0.44 volts, and it needs to be an oxidation half reaction, right? It needs to be an oxidation half reaction that's more positive. What could we use? So, well, go this way, that's not more positive. That's only going to be positive 0.4. So we need to go this way. This is a possibility. This is a possibility. Zinc solid or chromium solid. Now, chromium solid produces chromium ions, and that's really bad for the environment. So, not that one. Zinc. Zinc solid would be the one to use. Right? And that half reaction would look like this. Zinc solid going to zinc plus 2 electrons. So that's what they do. Because zinc plus 2 is not bad for the environment. That's okay. We eat zinc. So those are zinc ingots. So these are nails that I put in water about 4 years ago. This is a nail, just a regular nail, and this is a zinc-coated nail. So you can see that after the course of 4 years of being in water, the uncoated nail is rusting up pretty good. There's a good hunk of rust on the bottom. But the zinc-coated nail, it's the zinc that's reacting. Right? So the zinc coating is still even on the nail. So it's protecting the iron underneath. Sacrificial anode. What is the standard cell potential you would obtain from a cell at 25 degrees Celsius using an electrode in which an iodide solution is in contact with iodine solid, and an electrode in which the chromium strip dips into a solution of chromium 3? What is the standard cell potential? So what we're going to do is we're going to use this information to figure out what our two half reactions are. Find out what they are, right? Figure out what the E zeros are, and then add up the E zeros, and we'll have our answer. That's our game plan, okay? Let's see if we can figure these out. We've got I minus and I2, okay? So that's definitely going to be this half reaction. Here's one half reaction. Let's identify the other half reaction. Chromium strip, that means chromium solid, and chromium 3. Very bottom. Okay. I have to flip one of these reactions. Remember, all electrochemical reactions, one reactant produces electrons, the other reactant accepts them, reacts with those electrons. Something's reduced, something's oxidized. And we want to set things up so that they're the most spontaneous. That means set things up so you get the most positive E0 cell. So that means let's leave this one as is, but flip this one. So we'll have positive 0.53 for the iodine, and for the chromium, chromium solid, positive 0.74. And they just asked for the standard cell potential. They did not ask for the overall reaction, just the standard cell potential. So just get E0 cell, and we're done. So 0.53 plus 0.74, 1.27 volts. It's my E0 cell. What is the standard change in Gibbs free energy for the following reaction? Use data from a table of standard reduction potentials to solve. So here's our reaction. Find the standard change in Gibbs free energy. We only have one equation we can possibly use, so not much choice there. But let's take a look at it. We need to find, well, we know what F is. That's just Faraday's constant. We need to find N, the number of moles of electrons that cancel, or the number of moles of electrons that transfer, right? Same thing, and E0 cell. So that means we need to find those two half reactions and add up their voltages and get E0 cell. So what two half reactions would we be adding up so that we get that overall reaction? This has to exactly match, right? It must exactly match. Okay, so what are we going to add up? I minus has to be on the reactant side. So that means we're going to have to flip this one. We'll have to flip that one, right? So let's flip it. We'll have 2I minus goes to 2 electrons plus I2 solid. And my E0, to flip it, so it's negative 0.53 volts. Now we need chlorine gas and chlorine minus. Here it is. So let's just write it as is here. We'll have chlorine gas goes to, well, plus 2 electrons, goes to 2 chlorides. And my E0 there is positive 1.36. Okay? So when I cancel these electrons out, you see how many electrons are canceling? 2. So my N is going to be 2. That's how many electrons canceled out when I added up these overall reactions. E0 cell, 0.53, it's negative, plus 1.36, about 0.83 volts. There's my E0 cell. Now, we should probably check to make sure this matches. If I add up these two reactions, I get 2I minus plus Cl2 forms I2 and 2 chlorides. Does that match? Yeah, that matches perfectly. So the reaction's good. Okay, so now I'm ready to find my standard change in Gibbs free energy. That's minus NF E0 cell. Minus N we said was 2 moles of electrons. F is 96,485 coulombs per mole of electrons. And E0 cell is 0.83 volts. I get about a negative 1.6 about times 10 to the 5th joules. Because a volt times a coulomb equals a joule. So I get joules. Negative 1.6 times 10 to the 5th joule. Calculate the equilibrium constant K for the following reaction at 25 degrees Celsius from standard electrode potentials. And here's our reaction. So how are we going to get an equilibrium constant out of standard cell potentials? Right here. We need to use the tables to get E0 cell. From the half reactions, figure out how many electrons cancel. We'll get N, and then we'll solve for K. So E0 cell equals 0.0592 all over N log of K. So let's find out what those two half reactions are, so that when we add them up, we get this. And it has to be exact. So what two half reactions are we going to add up? And we can write our E0s over here. We need 10 plus 4 on the reactant side. There it is. And it's already on the reactant side. So we need this half reaction. 10 plus 4 plus 2 electrons goes to 10, 2. And my E0 is a positive 0.13. Okay, so there's my 10, 4 going to 10, 2. Now I need mercury liquid going to this mercury ion. Okay, that needs to be an oxidation half reaction. So here's mercury liquid going to that mercury ion. So I need 2 of them. Going to the mercury ion and 2 electrons. And it's a positive point. I need to flip the sign though, because I'm talking about an oxidation half reaction now. Negative 0.85 volts. So let's make sure this is going to work. The electrons cancel, so my N will be 2. I'll have 10, 4 plus 2 moles of mercury liquid form 10, 2 and a mole of that mercury ion. Okay, looks like it matches. So I've got that part done. What's my E0 cell? 0.13 minus 0.85, about negative 0.72 is my E0 cell. So let's plug everything in. All the negative 0.72 has to equal 0.0592 over N, and we said N was 2 log K. So bring those numbers over to the, we'll have 0.72, it's negative, times 2, divide by 0.0592, it equals, raise it to the 10 power, about 4.7 times 10 to the negative 25 is my K. A very small number. And it is so small because E0 cell is very negative. It's a very non-spontaneous process. If you want it to go, you actually have to put energy into it. Okay, so I think the main idea of everything we did today was that when you look at these tables of standard reduction potentials, that you realize whether it's an oxidation half reaction or a reduction half reaction, they all happen with different degrees of spontaneity. And that's all recorded right here with those E0 numbers. The more positive that E0 is, the more spontaneous that reaction is going to be.